All right. So yeah, as Bruna briefly introduced me, I work as a security scientist, actually as a principal security scientist out at H2O. My primary job is to basically architect and build solutions that that include models which try and detect malicious behaviors across the internet. It could be anything to do with financial fraud, it could be do with electronic fraud or networks or any of these things. And the general idea that I want to take today across my slides is how do we go about building it? What are the thought processes that actually go in it? What are the key components that we look for? And what is important for you to look as well in case you're building models for malicious behavior. Quick question, how many of them here out there are like data scientists or ML engineers who do this on a day-to-day job? Great, okay, quite a few number. How many of you guys out here work in the field of security? Oh wow, okay, fair. That number usually never is bigger than 2. I'm actually happy it's about 5. So yeah. So quick set of slides about H2O. How many of you guys actually know about H2O? Curious. Okay, so this seems pertinent. So we are based down in South Bay, out of Mountain View. We've got a good amount of money, and then we are about 200 plus people in the company, a good number of cattle grandmasters out there who help us build models. The company comes up with a lot of engineers, a lot of scientists who work in many different areas. We are primarily a machine learning platform company. And we build quite a set of tools which help people build machine learning models for many different use cases. And I primarily work for the securities solutions group. Now, we've got offices based out of across the world, good part of the world. Let's put it that way. In case anyone's interested, thinking of joining us, please contact Bruna or me. Be happy to help you guys out. A set of our clients, how good we are in the community, and that should be good. And we primarily have 4 different products that we, I would say that the company puts out. Driverless AI is our current flagship product, which actually automates a lot of machine learning processes that you usually used to do. H2O and Sparkling Water are actually the open source variants of machine learning model building. H2OQ is slated for the end of Q1. It's actually a new platform that we're building, which helps us build models much better with insights and modeling together coming onto one platform. So that's like an integrating platform that we are currently building, which brings in, at the same spot, you can build models and insights at the same time, which seems to be like a pain point currently in the machine learning field. And all right, so that's set of slides about the company. And this is a general structure of my talk. I'll talk about the problems that usually we look at when it comes to identifying malicious behavior. I look at what are the kinds of data you necessarily need to have. How do you look at the modeling process itself, the feature design, and the modeling design itself. Now, having said this, I would urge you to have, call out and ask me any questions that you have at any point in time. Completely okay with the idea. If you want to hold it till the end and get this set of slides and see if your questions get answered, fair too. Either ways works for me. Don't worry about it. I'm happy to answer anything. So, generally speaking, what is it that we are looking at malicious behavior? What are the kinds of malicious behavior that we are looking at? There are many different kinds of malicious behaviors. You could have some of them, that are problematic for you that we have listed on the fields right here, or there could be other things as well, like someone breaking a traffic rule. That's not necessarily the kind of things that we're concerned with when it comes to the modeling that we're building right now. We are essentially, actually, give me 1 second. Can you guys look at the screen from there? Is it possible for you guys? Maybe you guys might want to scoop in or come on. Okay, great. That's fine. So there are various sets of malicious behaviors that we actually look at when we build models. A good number of them is comes in the field of electronic fraud, where there are many different kinds of frauds that actually happen. There are people who've stolen access to accounts, and then they're doing transactions in someone else's name. Then there is usually impersonation and phishing. This is one of the biggest use cases that we deal with, where I've sent you an email saying I'm the king of Nigeria and I need your account, and that's usually how it goes. I'm sure everybody knows about it. And then the usual, the credit card fraud. Someone used your account in the middle of the night at 3 a.m. You would have never done it, because you sleep at 9. Well, that's a problem. Then you have the usual transaction fraud. I would have actually gotten access, to your account by some surreptitious means. I would have gotten onto the darknet, probably gotten access to some of your account information, and then I come back and use it before the bank, and you figure out I've drained all the money out of your account. The last one, which is personal but unknown transactions and phishing, is actually one of the most interesting use cases that we deal with. So essentially, what happens in this type of malicious behavior is actually, let me put it a different way. What a lot of people have figured out is that stealing your passwords or stealing access to your system does not make sense, because at the end of the day, you get discovered. So if I were to steal your account usernames or passwords, some point in time, 10 days later, 20 days later, a month later, someone will figure it out, and then their account gets blocked. What a lot of people do is they run access to your account through your machine when you're up. So basically, all your credentials are captured, kept in your system, and then they run it from the same system, so as to not create any suspicion to the bank or to you as a user. So that's probably one of the most interesting use cases that we deal with. And the way we work in all these things, we work with many different financial institutions and interesting agencies to try and deal with this problem. And we usually see quite a few variants of these things, but much of these things actually involves trying and predicting any of these frauds happening around the time or just after it's happened. And that's essentially what we build models for, and that's what we're trying to solve out of it. Now, your malicious behavior can be classified in two forms. One of the things is it's actually criminal, in the legal parlance, if you're looking at it that way. And the other one is it's actually, if you look at it statistically, if you look at it merely as an aspect of the data, it is not normal. Essentially, there is something out of the ordinary that stands out, or that should stand out. Let me correct it, because a lot of this kind of data tends to seep into the family and don't necessarily stand out. And that's essentially what we're trying to find out. It's not the first problem that we essentially deal with. That's for a lot of law agencies and law enforcement agencies to work with. We deal with the second problem, where we can, and by dealing with the second problem, we tend to give enough information in case someone wants to go towards, legal procedures. Now, one of the most important things that you need, when you're looking at malicious behavior, is the data that actually supports the kind of modeling that you're doing. A lot of people work in security right now, and do you guys have like the best kind of data to deal with in terms of any kind of identification that you have to do in attacks, or are there shortcomings that you actually face?
Yeah, shortcomings.
And what kind would that be?
I mean, new abuse vectors come in every day. So we don't have the data. We create a model based on older data. After new kind of abuse comes in, our model is not looking at that.
Fair enough. So this is not necessarily a problem that exists, in the field of security itself. This actually exists in many different fields. Your data must, complement the kind of model that you're trying to build. In a very fundamental sense, you kind of have to figure out what you're trying to detect. Are you trying to detect individuals, who are showing up fraudulent behavior, or you're trying to create, are you trying to figure out clusters, or put it in a very simple sense, are you trying to figure out groups of accounts that are kind of operating in a certain way? Let me give you a very simple example. You could have let's for example say that a bank tends to have some kind of a vulnerability, and using that vulnerability a lot of accounts might actually be compromised. So when you compromise a bunch of accounts, then eventually what it leads to is all those compromised accounts tend to behave in the same kind of way. In those situations, you are expected to try and identify the clusters of those accounts that actually stand out than your normal banking accounts. Or in some cases where only one individual's credential has actually been stolen, then you're looking at those individual credentials to try and identify, this is the one that actually stands out. And that's essentially one of the things, do you have enough information to identify an individual, or do you have enough information to actually identify the cluster or the groups that you're looking at? The next thing is, how quickly do you want to determine, if there is a breach or if there is a malicious behavior that's actually happening? And this could very well depend on your risk team. This might not be up to the data science team, or this might not be up to the business team as well. This usually comes from your risk organization, where they say, we are okay by taking a damage, for about a day, or we are okay to take damages for about an hour or a minute or so. And based off that, your models will be designed in a way where you're predicting, activities when it's happening, or you're predicting activities when it's just happened, or at the end of the day. A lot of use cases that we deal with, and some of the use cases, I'll give you a simple example. One of the use cases that we deal with is fast credit card transactions. So fast credit card transactions is where a person has actually gotten access to your credit card information, not necessarily the physical card itself, but the actual credit card. And they can actually make a copy of the card. They can go to a different location, extract as much money as much as the ATM allows, and quickly get away with it. So essentially what happens is, under those situations, you can't actually identify it immediately, but you get to identify it at the end of the day. So there are different kinds of behaviors that you can identify immediately. There are different kinds of behaviors that you can identify in batch. Now it's also a negotiation between how much of a risk you hold and how quickly can your models detect. Now your models might be super good. They might be extremely good, with a very high ability to detect these behaviors. But the other problem that stands out is your model super heavy to actually detect these things? If you have 10,000 features, or if you have like 100,000, can't be 100,000 features, I would hope not, maybe like 1,000 features, then you would have a problem because the model will take much more time in identifying these things. So at those times, there'll be a bit of a compromise where your risk will have to say maybe 5 minutes, and the model will have to scale down in terms of the features that you actually put into the model. And that's essentially the question, is the data available actually at line speed? And then comes the much deeper question, have you joined all the relevant tables to make the decision? If not, can you do it at line speed? One of the bigger ones is, how robust is your model? Now, we understand that the model building process itself has been commoditized. And what do I mean by that? Your model is not the loved one that you keep it to yourself anymore. You build a model every day. As and when behaviors change, you tend to build newer models, you tend to build it faster, and you tend to implement that really quickly. And that's essentially what is happening right now. And you actually have to do it because the terrain in which these kind of behaviors actually exist change very frequently. It could change within a day, it could change across a week. So that means that you have to be quick enough to build newer models to be able to try and detect this behavior. But for you to actually have the kind of robustness that you expect in a model, you need to have enough data. Is the data big enough? Is it long enough? Do you have a good enough history for about 8 months a year? Usually 8 months a year is a good enough number, depending on the kind of behavior that you're looking for. Or all you have is just 3 months of data. And we routinely see a problem between different agencies we work with, and this is not something, that I kind of write it out as something that I just think about as a natural problem. But this is routinely a problem that we face when we work with different agencies. A lot of agencies do not actually have access to data more than 3 months, which means that the data that we're working on is in much lesser time, which means that we actually have to build robustness into the model within that period of time. So there we go. So now you've got your fundamental sources of data. Now, are there additional sources of data that you can look at, which would probably provide you supplementary information that you can use for your decision making? For example, can you look at web server logs? Can you look at network logs? Can you look at your application logs? Can you look at your account access logs? Now, again, mind you, adding a lot of information can give you a fantastic model, but that does not mean that gives you enough speed, the ability to be actually proactive in trying and identifying this behavior. And you might be seeing a subtle idea that I'm trying to throw, that you kind of have to be really fast. And that is the kernel of, or the crux of how you deal with malicious behavior. It's not a model where you're trying to figure out, does this person get a loan or not? The person probably can wait for a day, if someone wants a loan. In trying to figure out this behavior, there is a lot of loss that is associated with it, which means that you are on the clock every time a certain behavior actually happens, which means that you actually have to make very conscious decisions about how big your model is, how many features are going in, what is my risk factor, how much of data I can actually bring in. And that essentially puts you in in kind of a good and a bad squeezy spot where you kind of have to make these decisions before things go into implementation. So I'll come to the next set of the actual what we do here is features. Now, one of the biggest things that you have to decide when you're building up features, or rather, one of the biggest things that you actually have to make a decision when you're building models for malicious behavior is trying and building the right set of features that helps you identify whatever you're trying to identify in this case. And the features can be largely divided into two groups. These are not purely exclusive. They kind of overlap with each other. There is the individual, and then there is the population. Essentially, the reason why you're building this is you're trying to build a population characteristic. You're trying to see how are all the members of your financial organization or your agency that you're working with, what's the normal behavior that they usually carry. And then you are trying to identify what is the individual behavior that everybody carries. Now, when you're using these two as a comparison metric, you're trying to see how much of a variation is there from the individual to the population, from population to, let's say, 3 months before, or from individual to 3 months before, or a week before, or a day before. That's essentially how you try and identify if there is a variant across here. And there are three primary, very, very fundamental feature families that you look at for these individuals and activities. These three feature families are attributes and activities, of course. You are also looking at interaction between entities. It could be a population, it could be a systems interaction, it could be an individual's interaction, and that's essentially what you're building. And finally, networks. You're trying to see, how does a larger system, how is it actually working? Like, what are the kind of interactions that's actually leading to egress and ingress? And I'll give you a few examples, and probably that'll, illustrate these things much better. So, let's say you're looking at a single individual, and you're trying to establish a baseline. And when you're trying to establish a baseline, you're trying to find out, what are the kind of behaviors does this person naturally, espouse? You're trying to see, does this person naturally, transact using cash, or is it usually credit? And that's essentially to establish what is the kind of instrument that this person usually uses when they're trying to do transactions. Then you're trying to see what is their natural set of interactions? What is the natural course and set of interactions that they do on a daily or a weekly or a monthly basis? And that essentially tells you how periodic or how non-periodic is this person in terms of their activities. So this is actually one of the bigger clues that you get when you're trying to move, to actual interactions between different people. Then you're trying to see, what is the geographical identity? And with geographical identity, I don't mean race. I actually mean what is the IP address you're coming from? What is your usual activity location? What kind of activities do you conduct from a certain kind of location, for example? Let us say I'm applying for a new credit card. I would probably not be applying from an airport terminal. I would probably be doing it from my house, or I would probably be doing it from a residential location. Because those are the kind, there is a certain association with when you do these kind of activities. And you also try to see the periodicity of where you come from. Is this person naturally residential? Does this person conduct their activities, from their office as well, or usually when they're mobile? And essentially, that is what establishes the kind of probabilistic score that you can associate with in terms of how much of a risk you can provide. How does their social identity fit? Now, you can take information that you probably you can get from social network graphs, and you can bring that in, and you can say, how many people does this person naturally interact with? Is there a natural? Is there a sense of a lot of interactions, one-off interactions, periodic interactions, or complete randomness? And that is something that you can establish when you're trying to identify a social identity of the person as well. Then you're looking at different kinds of ingress and egress, and this ingress and egress can be of many different kinds. In this case, we'll probably just focus on the financial instrument. Now, if you were to look at my bank account, the only way of ingress that I get in my financial account is my paycheck. But then there is egress for natural utilities. There is egress for like credit cards. There is egress for different kinds of payments that I necessarily have to do. With that too, you can establish a certain kind of periodicity, and then you can say there are some that are not necessarily periodic, but are not necessarily risk-worthy because they're not that active. You can also try and see past triggers. Now, past triggers are actually one of the biggest identifiers that help you detect whether this person has a natural position to actually commit interesting behaviors. You would look at, let's say, how many times has this person triggered off, or how many times has this person triggered off a loss of credit card. If there is a loss of credit card, then the risk quotient for this person can actually be higher than the rest of the family that you associate with. You can also look at volume rates in terms of what is the rate at which this person operates in terms of their amount. You can also look at the amount of volume itself. You can look at that as well as a measure of how risky or how not so risky it is. Operational window. The idea is very intuitive. It tries and finds out when are you actually active. A lot of people tend to pay bills, tend to pay credit cards and all these things over the weekend. I mean, we don't necessarily do all these things over the weekday. And that essentially, puts you in a separate group. So you can establish, this kind of information as well. Now, the thing is, with all these identities that you establish, you can also establish a second form where you replace the individual by population. So where you segment the data and you say, okay, this person belongs to this group. How does this group naturally operate? How is this person? How much of a variant is this person from the group that we expect them to belong? And that will essentially give you two kinds of measures. It will give you a person's measure. I mean, it will give you, of course, the population metrics population statistics for all these things that you measure. And then it will give you the individual statistics, which you can use and compare and try and find out, how much of a risk quotient you can actually associate for this person. So the next set that we look for, again, is interactions. Interactions are Another beautiful set of features that we use, which are actually super useful when it comes to predictions. Sometimes we don't necessarily have a good amount of individual or population statistics. At that time, we use interactions as interactions tend to stand out, as good features when we're building these models. So in interactions, you're looking at age groups. What is the? Did you have a question? Sorry. So in interactions, we're looking at different kinds of age groups. Different age groups tend to operate in different ways. Usually, age group of 50 and higher, maybe not 50 anymore. I would probably say about 60 and higher, tend to operate much more in cash, where what you see is. So you kind of have to be watchful also based on the kind of instruments that you're looking at. So for example, a person might actually withdraw cash and give it up to someone, and on the other end, the person might actually get cash into the account. So although that's not a detectable link, with a probabilistic measure, you can say that this amount was essentially transferred to this person using cash. So for that, you can actually use different kinds of metrics where you say, how you can use the ingress and the egress, where essentially you try and identify how much of money is actually coming into the account and how much of the money is actually going into the account based off the instruments that the person is using. So one of the indicators that we use to try and segment across the group is age, which tends to help us identify different age groups and clearly figure out what's happening out here. Loyalty, not a subjective thing. It's not brand loyalty. It's more like how long have you had this account, and let's say how many people have you actually tried to bring into the financial institution or the agency for that matter would be an interesting measure. Many number of years, you tend to have a low risk score. Not necessarily, so many years. We don't necessarily give a low risk score, but we definitely associate a risk factor with that person. Then we also look at, excuse me. Then we also look at the periodicity of interactions. How frequently do you pay your kids? How frequently do you pay, like, let's say, the bar ticket or any of those things? You also look at seasonalities. Every time the Super Bowl happens, a lot of people put in bets, which essentially means that a lot of money starts to move into certain kinds of accounts. That is not necessarily dangerous. It's just a seasonal thing. And one of the other things that we also see is this is especially in North America. We see that when it's summer, there tends to be a lot more activity in terms of transferring money because people are traveling and they're trying to share money or pay back or something. So that so seasonality tends to increase the amount of interactions as well. And there is also system interactions. How much of this entire system tends to move periodically? Do all these people interact? Well, were they all interacting for the last 3 months? Were they all interacting for the last 6 months? Were there any new entities? Were there any old entities? Did things change? Very similarly, you also look at the volumes, trying to see how much of this interaction tends to carry over a year or 6 months period, a month. You also look at the interaction rate. How many times does this person actually interact with another person? Now again, just like how we did for an individual, you can also look at interactions across a population. Now the interactions in population is very interesting because individuals, it's very easy because there are individualistic attributes, you can cluster them and that it ends there. But across populations, you're not only looking at intra-cluster interactions, but you're also looking at interactions between clusters. So that essentially puts you in a very good spot to try and see, how mobile is this person how mobile is this interaction from one cluster to another? And that essentially gives you a good measure as well. Now, mind you, these two sets of things that I'm actually talking about are the kind of features that you actually build for your model. Now these features actually go into your model and help you figure out if something is actually a real transaction or something is actually a fraudulent transaction or some kind of a malicious behavior in the system. And that's essentially what we're getting to. Now what you've seen in the first set is interactions of individuals or specific set of population. Here you look, attributes of individuals or specific sets of population. And here you're looking at the same set, but you're looking at its interactions. The next one is actually a bit more interesting, and where you're looking at a network. Now, this tends to kind of blow up the problem just a bit, but it also gives you a lot more information in terms of what you're trying to find out. One of the biggest things that you're trying to find out is this network convergent or divergent? And the reason is a lot of money laundering techniques, fraudulent transfers of money tends to have convergent networks. So there'll be 10 people. How many people here have actually heard of a concept called smurfing? Great. So it's not the smurfing in the network sense, it's the smurfing in the financial transaction sense. But it's the same principle. So the idea is very simple. I don't want any financial institution or any organization to actually detect that I'm transferring like $10 million. And what I do is, for about 1,000 people, I break up that $10 million and give it to them and ask them to deposit into their account. And after a set of days, I ask them to transfer it to another person X. Each of them will have, like, let's say 1,000 people. It'll converge to a 50 people network, and then 50 people eventually converge to, like, let's say 10 people. And these 10 people tend to actually withdraw the money, and then it's taken out of the system without any detection. That's actually fraudulent. That's a form of money laundering, which entitles you to get a very fantastic criminal case. But that's, of course, the other side of the story. So those networks tend to be fraudulent. So those type of networks tend to be convergent. Because one of the things that people who are actually conducting these kind of exercises, what they want to do is they just don't want to leave the money in your bank account. They actually want to take it out. And which essentially is like, it's like their Achilles heel. So if we can catch them at a point where the networks are convergent, we exactly know how things are converging. And if it's a normal operational behavior, the networks don't necessarily converge. Yes, of course, it converges to PG&E, but PG&E is not doing money laundering. We know that. But so that's essentially how things work. So which is one of the reasons why we look at larger and larger systems. So you can look at this at different sizes. You can look at the convergence or the divergence of a network across segments, within subsegments, or within clusters. So you can look at it in many different ways to try and identify how is this entire system or network actually moving. And you're also trying to see, what is the operational periodicity of these networks? Is this transaction a one-off thing that's actually coming into the network, or is it periodic? Does this kind of money actually move across the network periodically? You also try to see what is the active time. How much across a given period of time is the network actually active? How much of activity does this person tend to have? And you can look at something that's very interesting. It's called lock level. So lock level is nothing but it's just like a window which you use to actually look at different parts of the network at a given period of time. So you're looking at many different areas across the network to try and see if something that's actually coming out of a part of the network that we are looking at, is it actually getting in whole, or a big chunk of it, is it actually getting into a different part of the network as well? And that essentially tells you that this network, that these set of individuals or these set of clusters are actually operating as one network. So if you're lock level mapping, so if essentially, let's say, 3 people out here and 3 people out here are not necessarily transferring anywhere close to, like, let's say 80% to 120% of the money that they've got within them, then essentially you can say that they're not necessarily in the same lock level, and that helps you try and identify whether they're part of the same network or not. And you're also looking at any recent changes in behaviors. Did they add, did the network grow? Did it grow, in a much larger fashion. For example, this is probably going to be very interesting. Across Europe, one of the things that we see dead people coming back, and that's not necessarily a cool thing. It's just accounts of dead people actually comes back. That's all. There's nothing else to it. And what happens is there are times when these accounts actually come back, and the number of people in a network actually increase. There's a really large number of people that that swarm the network, and then you see that there is a lot more activity than you would expect it to be, and those are kind of the recent behavioral changes that you're looking at. Then you're also looking at one of the things that you also want to do is you want to try and find out who are the probable set of culprits that are sitting on the network. So you're essentially looking at like the last egress point. Where is this money actually coming out, or where are these transactions actually converging into? And that's essential. Is it the same person all the time? As I said, it could be PG&E or it could be an actual person. If someone is malicious, the egress points tend to change quite frequently. So that essentially gives us an indicator to try and highlight and say, this person was the egress point for this network 3 months ago, but the same person is not the egress point for the network anymore. And that change actually helps us identify that there is this interesting behavior across this network. So one of the last things, of course, probably one of the most valuable things that we're looking at is pass-through to origin ratio. So essentially, how much of transactions, it could be volumes or it could be merely counts of transactions, so it could be volumes or values. How much of money actually passed through the system, how much actually got retained in the system, how much actually converged much before the egress point in the system. So that gives you a good indication of a segmented set where either there is a lot of fraudulent transaction happening in it, or it's not necessarily fraudulent, it's just a divergent network and everything seems to be hunky-dory. So as I said, let me quickly jump back to this. So as I said, there are 3 primary things that we try and build when we're looking at malicious behaviors across financial transactions. Attributes and activities. This could be individuals or populations, interactions, and networks. Yes?
How do you go about trying to demarcate a network or find the boundary of a network?
So that's actually a fantastic question. I think for people who couldn't figure out how do you demarcate the network is the question. So the idea is we use natural segments to first try and identify if the behavior seems to be intra-cluster. So within a cluster, does the behavior tend to be the same? Does the behavior tend to pass over to another cluster? So we try and figure out if the clusters are exclusive or there is some crossover in terms of behavior. If there is a crossover, then we recluster. It could be, you could also have a large cluster which could be subsegmented, but then 2 segments of 2 different clusters could be the same. So then we recluster them as well. So this part, I would actually say, is a much more trial and error and a much more like a statistical problem rather than sure shot, here you go, this is a solution. So you kind of have to look at the data and you have to do it multiple times to get the right set.
Is the starting point institutional boundaries often, or demographic or geographic region, or is this sitting too close to home?
Okay, so that's actually a fantastic question as well. The starting point, we use both because we work with organizations around the world. We tend to use geographical boundaries as a natural starting point for us, but then we automatically introduce the institutions as well as a next subsegment for that. Yeah. So I'll switch to the next part. If there are no other questions, I'll just switch to the next part, which essentially speaks about how we look at the models as well. And one of the reasons why we're looking at models is we tend to have a lot of data scientists and machine learning engineers who work with me who tend to say, oh, I've got this to 9.5 or 9.7. How do I make it 9.8 or 9.9 or whatever? And something that I very strongly believe in is those numbers don't actually matter. What matters is, how much of a problem are you solving based off the risk factor that your institution actually gives you. So if you're working within the risk, the risk limit that your institution actually provides you, then you're fine. But you can, of course, improve the modeling by making better features, by probably tuning your model as well. Because to be fair, almost all modeling techniques right now tend to be really good. And especially for trying and identifying malicious behavior, I would say that I have found good and bad results with all kinds of modeling techniques as well. So there is no one go-to model, but I would say everything works the same way. But of course, I do a lot of random forest myself, just because I like it. That's about it. There's nothing else to it. So in terms of the model, there are a few fundamental questions that actually comes by. One of the fundamental questions that, of course, one of the things is, what are you actually trying to solve, in this case? Are you trying to solve an ML problem, or are you trying to solve an AI problem? There is a chasm between these two, and we don't necessarily try and, figure that out. We tend to say, we tend to speak about it in the same breath, and that's essentially not fair. And I'll probably speak about it just a bit. But if I were to put this question out to you guys in the audience, how would you look at it? Are you guys solving an ML problem, or are you guys solving an AI problem? Anyone could. It's perfectly fine. The mic is free.
Are you trying to differentiate between the research problem versus?
Not exactly. No. So, all right. If nobody wants to take a dig at it, I'll try and I'll speak about it. So the idea with, actually maybe the next slide might help. The idea with ML is much more, is much more just classificational. What you're trying to do is you're getting a model to actually learn a certain set of behavior, and then you're using that to predict a certain set of behavior. In AI, there is a bit more to it. You're not just, the whole process of ML seems much more linear. As I said, if I were to give you an example, very simply put, in ML, you're just trying to find out whether it's fraud or not. You are essentially concerned with the very simple decision that you've given it a set of data, and you want to try and find out whether there's fraud happening, or this transaction is fraudulent, or this transaction is not fraudulent. It's a very linear problem. And what essentially the question you tend to ask is, what is the classification, or what is the group that this transaction actually falls in? And this problem actually is very linear. It doesn't necessarily give you any insight into what you're looking at. Your model doesn't necessarily carry the insight. It's just, I've learned a set of things. Based off these set of things, I know how to predict. And that's essentially what your ML problem is. But when you switch the same thing to AI, the solution is actually emergent. What you're trying to do is, you're not just trying to classify whether it's fraud or not, but you're also trying to classify what kind of a fraud is it. Like it's answering a much more, much more deeper question. You're not only using the data set, you're not only using the features and the techniques that the domain knowledge and all those things that you've got to answer the basic question, which is this fraud or not? But you're also trying to identify, is this actually a certain kind of fraud? Or if you want to put it in a way, what type of fraud, or why is it a fraud? That's essentially what you're trying to identify. So there are two, fundamental differences out of it. I think David Deutsch probably does a much better job in explaining what emergent is, so I would probably refer you guys to him. But yeah, that's essentially what you're looking at. And that is what you're supposed to do. And if you're looking at merely, a machine learning problem, then a very simple model that helps you classify if it is a yes or a no makes sense. That's about it. That's essentially what you should be looking at. But if you're looking at a problem, which is much more AI, whether you're trying to find out, is this impersonation, or is this transactional fraud, or is this, personal fraud but sitting on your machine, any of these things. You are looking at much more sources of data or much more feature sets, a very rich set of features that actually make sense, from a domain point of view. You're able to understand what these features are. You're able to, help yourself classify. You're able to actually identify what this behavior is, and that essentially makes it an emergent problem. Does yes, please. Yeah.
So the idea is, if it's an AI problem, you can automate the decision making associated with understanding.
Absolutely, yes, yeah. It really puts you much more far away from this. It puts a bit of a distance between you and the system. I don't want to say puts you far away from the system. That sounds a bit scary. We don't want that. But yeah, it puts up a bit of distance between you and the decision making, because the system itself is intelligent to make that decision.
It allows you to walk away.
Yeah. I think there was another question. Oh, okay. Yes.
Is it like there is another ML problem after a bigger ML problem?
It actually is. Yes, you're absolutely right.
So why would it be AI? I mean, it's just ML, right?
So that's a fantastic thing, and this of course is subjective, and that's essentially what the idea of emergence is. It's much more than the composition that it actually has. So your problem could entail many different models eventually by the time you actually get that intelligent decision making, or it could be just two models, and your system that you build, with all these models could be smart enough to actually make that decision. But you're absolutely right. It could take many models to get you to that point, or it could take you just a few models to get you to that point. Yes?
You also use like a multinomial technique for AI instead?
I would beg you not to do so, because the only thing that happens is when you're using a multinomial approach for problems of this kind, it tends to flatten the problem. And here there is a sense of hierarchical approach. If you know the construct of how intelligence is created, you have data, then you have knowledge, and then you have intelligence, and then you have wisdom, right? So the number of models that you actually put out eventually puts you to the pyramid where you have intelligence. But if you kind of flatten the model, then you're necessarily just stuck at a place where you have either data or knowledge. So, yes.
Yeah, so I guess like what you're saying is ML is one specific model predicting one specific component of a larger system.
Yes, yeah.
The AI is the larger system, because here, what type of fraud is it? I could have maybe multiple labels of like fraud.
True, yeah.
Expanded upon beyond binary, so.
I mean, so for that, I'll actually.
That's still a machine learning problem, correct?
Sorry, say that again?
If I had 3 categories or 300 categories of what type of fraud, that's still an ML problem.
It is, of course it is, and that essentially goes back to what the gentleman was speaking, that it's actually a sequence of multiple models that eventually gets you to a point where you're actually making intelligent decisions. And I'll give you a very simple example of how this approach is, right? You have a model which actually is telling you whether this transaction is fraudulent or not. The model is not smart enough to actually identify what kind of transaction this is, or what kind of a fraudulent transaction this is. You might need another model with an extra set of information which is capable enough to actually classify what kind of a fraudulent transaction this is. And that's essentially, it's like a chain of models that will eventually get you a point.
Yeah, that's clear.
And that's essentially how we build it. That's essentially how we build the system, because a lot of the decision making that financial institutions want, who essentially work with us, they want to try and keep as much as possible to an objective view. In the sense, they want systems to do these things as far as possible. And that's essentially what we're trying to build when it comes to identifying malicious behavior. And there is a genuine reason why they want to do that. It's because everything is becoming electronic. We don't necessarily go to the banks anymore. Most of our transactions happen online. And so way back, I think in like 2012, like credit card agencies were running about probably close to 30,000 transactions a second. Now every day, every second, they tend to have about 300 to 400,000 transactions, per second, which essentially does not put you in give you, good enough cushion to put enough people to actually identify whether something is fraudulent or not. And which is one of the reasons they want models that can actually make these decisions themselves and come to a point where it says, hey, you know what, this is what I actually think it is. And which is why we actually take this approach of building the models. And having said that, you could have many different ways in which you do this approach. An ML problem usually almost always is a supervised approach. In whatever I've built, I don't necessarily have seen, like an unsupervised approach in the models that we've built, at least for fraudulent techniques. In AI, it could be a combination of both. And essentially, for this very example, for trying and identifying fraudulent transactions, we've built supervised models, the outcome of which tends to get fed into an unsupervised model, which we're trying to use and classify, what kind of a fraudulent technique is this. And essentially, of course, the whole pipeline has to be as lean as possible. And this is what we usually implement in most of the financial organizations that we work with. Sorry. So, having said that, this is like this is basically like a set of this is a slide where I'm trying to say like how our models have actually evolved. When of course we have started off, we went with the idea that we can solve the whole intelligence problem with one model. Then you build a model, but that doesn't necessarily get you to the point. So you necessarily scale down. So most of the systems in the current day, most of the systems across the world, actually I wouldn't say current day. I mean, a lot of them are switching. I would probably say about 2 years ago was super rule-based. There were many different systems which were extremely rule-based, which are trying and identifying, fraudulent transactions, money laundering, or any of these, malicious activities using rule-based systems. The problems with these rule-based systems were you could very easily skirt around this, and you could miss the detection, which means that it was very, very easy for you to get through the system. So the way we evolved it is we took up the rule-based systems, we built feature sets, we built the model tuning parameters, and then we used classification checks. So for classification checks, we actually put a human being in the system, to try and verify whether a certain set of classifications were actually doing a good job or not. We used that techniques to actually rebuild much better models, and essentially, we are at a point where we've done the classification of ML models using these techniques. So from a pure rule-based systems, we have moved to a classification model. Now, the next approach that we have actually built as well is like self-discerning models. Models that are actually smart enough or intelligent enough to actually tell us what is the kind of fraudulent activity that is actually going on. And for this, we don't necessarily need classification checks. We have built enough learning that actually comes out of existing models, but we still use the features, the set of features that we actually spoke about. We still use parameter tuning to try and tune, the model to our risk factor, best specification. And we've come to a point where, where we have models that can actually make a decision on their own. I wouldn't say they are super intelligent. I would probably say, they are intelligent in a very narrow way. Very humbly put, I would probably say. They probably can't do anything else other than trying to identify, 10 sets of fraudulent, or maybe say it doesn't belong to any of these 10 sets. It could be that one more new set of fraudulent, activities that I am not able to classify, but you need to take a look at. So essentially, that's where we are right now. Maybe we'll see some more, development in the future. Having said that, I think I'll probably stop here and I'll open up if you guys have any questions, anything at all, comments. It'd be great to say that. Thank you. Yes.
So 2 questions. One, are there certain combinations of integer values, not necessarily, like obviously if there's a huge amount or very small amount, that could be anomalous, but like actual numbers that you just don't see in combination or permutation very often as a transaction that seem anomalous?
I'm sorry, I think I missed after the.
Oh, so the example would be like, you'll see a lot of different transaction values, like 99 cents or dollars, or something like that. But if it's like a combination of numbers that you just don't see very often as a value.
Okay, so of course that I think is a fantastic question that leads us to some of the features that we build. So we also look at sequence of transactions. Like let's say you usually do 99-cent transactions quite a lot, and then you suddenly do a $1,000 transaction, or let's say even a $100 transaction. It tends to create a feature which creates, hey, you're seeing a sequence of transactions which is very interesting. This needs to be a feature, so let's add that in as well. So we do tend to add that as well, yes.
And then the other question was, is there certain things that are fraudulent or fraudulent trends that you train on, and you may catch them early on, but then you're not training on those anymore because they're less prevalent?
Okay, yes. So we tend to face that problem, but most of the institutions that we work with are not necessarily proactive, completely proactive. Partially proactive is how I would put it. So that means that we still retain trends that were there yesterday, but we still make the models kind of oblivious to the trends that were there. So it could have like two different models where one is necessarily just trying to identify something interesting, while the other one is trying to figure out, what are the trends that this fits in. Yes. Yeah.
Very early in the talk, you mentioned concerns around latency
Uh-huh.
and keeping that down. I'm curious, what are some of the things that end up being most challenging from a latency perspective, and how do you think about addressing those?
So one of the biggest problems that we face when we are addressing latency is having a comprehensive set of data, but not being able to bring that together to actually make a decision. And this is, if I were to put it down to a very simple problem, it's the problem of joins between many different tables. Like, how do I bring it together? So at that time, what we do is, initially what we used to do, we used to go with the idea that we join everything together, at line speed or just before, something is going to happen, and then use all the features to make a decision. But now what we do is we have initial set of models that will actually tell us what class of, problem this might be, what class of a fraudulent behavior this might be. That means that there is a selective set of features that actually get joined, not necessarily all the tables, and that helps us make a decision. So that cuts down the line speed, the amount of time it takes for us to process things at line speed. But that does not mean that we are still capable enough. After that, the next step would actually be curated set of features. So we restrict, for example, some of the models that we have built are about 1,700 features. They don't make any sense when we are making the decision. We use just about 110 features. We bring it down to a much more smaller level to be able to make the decision much faster. And that reduction is also a place where your risk teams comes and tells you that, hey, you've brought down the features to 110, but the risk is increased by a certain factor. We can take it or we can't take it as something that, it's a discussion that actually has to go through.
I guess a follow-up question to that would be, is there some sort of like offline model where latency, maybe instead of having 50 millisecond latency, you have, as long as you want for some batch job, where you'll go back and revisit these?
So yes, so one of the other things that we do is, this is an online model, right? I wouldn't say online, it's like near line speed. We also have another model which comes to, after the data comes into the system and we know it's been classified in a certain way, we have another model which builds all the features that we have actually put into the model and then reclassifies that thing as, right or wrong based off, what was classified earlier. So if there is a difference, it actually gets fed to a manual handler who puts it back in the system and says, this is where, your classification was wrong. And end of the day, end of the week, a new model building will be triggered. Thanks. Yeah?
I have a two-part question actually.
Please.
So before this, it's like automating the fraud detection process basically. So before this, we used to have a lot of people working in the fraud detection. how do you transfer that learning into your models?
Okay.
What are the factors to do? Second part is like, what are the new fraud detection people who are joining, who are still working in that field, have to learn to be above the system, or what new things?
Okay, so one of the things that we do is, one of the things that we've done rather is try and understand how people make decisions. Like investigators who have made decisions, we try and see what are the important things that they have actually made decisions. We don't necessarily take every aspect or every type of, I would say, assistance that they've used to actually bring it, make it into an object and bring it into the model. We use things that can actually be numerically or represented in a classificational way, and that's essentially what we bring in. If someone new is actually getting into this, to the investigative field, I would say it would behoove that person to actually try and understand how a model is actually classifying, because one of the new things there is a new problem that's coming out of this, and I don't know if a lot of people know about this, is wrong classification. Of course, the model is not perfect, right? So a lot of these the things that have been wrongly classified, or we randomly pick out of this set of classifications that we have, and we send it to manual handlers. So if these manual handlers know how things work, if he or she of course knows how these things work, and they can come back and identify saying this is wrong or this is right because of a certain feature that we put into the model, that would be like an extra set of skill that would be very valuable. Yeah. Yes?
Yeah, my question is on the classifying generation of feature set. So especially the network feature set. I just wanted to ask, in general, how do you guys generate the feature set? You have different classifiers that classify the set. If, for example, a convergent or a divergent, you just push in a set of transactions to a classifier, and it tells you it's a convergent and divergent, and you use that as a feature set, or you have one model and you push all the transactions, and then it will generate the feature set and give it a.
No, so we have one model that actually does this for us, but the network features that you talk about, so the network doesn't necessarily change at line speed, right? It changes in a much more slower pace. So we tend to pre-calculate this, much before, like at the start of the day, for example. We tend to recalculate this every 24 hours, every week, and we keep it ready. Sometimes what happens is there are places where we actually recalculate this every hour, which means that there is a set of functionality that's actually happening at another place where, new set of features are coming in. But some places are very comfortable by having these network features, for a day or for a week. Yes, yes.
My question is more from a business perspective.
Please,
like,
yeah.
Let's say you classify something as fraud or not fraud, or whatever other classification you're doing, and if I ask you like, hey, why did you say it's fraud? Like, how do you go back and infer like what feature was responsible for that? Like, how do you answer that question in plain English?
Fair enough. So if you actually look at it, let's take any of the features that we're using, right? Like, let's say there was some individual feature. I'd probably take network because that's probably some of my favorites. So you're looking at some of the network features out here, and some of these features actually come by and tell you that there is a certain reason why your transaction was classified as fraud, right? Now, if you look at convergent or divergent, for example, or if you look at, like, let's say lock level or recent change in behavior, these are intuitive features. These are not just combinatorial features that you build but you don't necessarily understand. These are intuitive features that you can actually take it to your business and say, hey, look, there are a set of entities in this network that actually have a convergent behavior, which is one of the reasons why, based off the network part of the features that we built for this model, it tends to say that this is fraudulent. Or, for example, a recent change in behavior, right? Like, the number of entities could have increased. Which essentially says that because of this, there is a complete change in how the volumes are actually happening in this network. And that is actually a true feature that you can take to your business and say, look, you understand what this is, and our model is saying that this is like an important feature. And that's essentially one of the explanations you can give.
So basically there is a human being that's sitting behind the model who is going through your 110 features.
No, there's no human being per se. There is a human understanding to it. So this is not just an X. And when you figure out why is your model classifying something as fraudulent, it's not saying because of X. You actually understand what X is. And that gives you legitimate reason for your business to try and figure out, oh, okay, maybe we have a problem here. Maybe we have a lot of money laundering networks in our financial organization. And that kind of gives you like an intuitive idea of what's happening. But if I replace this convergent and I just calculated a feature, let's say I blindly built features. All combinatorial, possible values that I got. I just built a feature and I threw it into a model and I predicted the model. How do you explain to anyone what that is? You would only be able to explain from a very experimental idea that this feature actually results in certain behavior. But now, can you say that that feature is consistently going to predict all the other behaviors? Maybe not. So which is one of the reasons we focus on like building features that are more like intuitive, more like understandable for a human being as well, and for the models. Because you also have to understand fraud and money laundering and all these things, right? There is an element of legality associated with it, which means that in a court of law, you will actually have to be able to prove that this thing is how it is. I can't just take a feature X and say, this feature X said this is fraudulent, hence we are filing charges against you. That doesn't necessarily happen.
So you basically want to build intuitive features and want to analyze them to give an answer.
We want to build intuitive features. We don't necessarily want to analyze them. But if there is a point where you need proof of why a certain thing, we classify a certain behavior, there is an intuitive feature for you to use. That's essentially what it is.
So
Yes?
does that
Yeah.
make like dimensionality reduction techniques like a no-go?
Yes. We do not go towards that at all, unless and until we are in such a bad shape that none of the features that we are building are actually making any sense. We have never ended up in that situation, and the reason is because what we're looking at here is malicious behavior, right? Which means that there is a human element in it. I mean, human beings are the only ones who do this. Systems don't do it. Every other living organism on Earth probably doesn't do it. I don't know. I don't want to say that. Fair enough. Yes. See, there you go. Which is why I said I don't want to say that. We know humans act in a certain way, which is one of the reasons if we build features that can identify which can classify these behaviors, it's comfortable for us to explain it. Yes?
Do you incorporate different costs for false positives versus false negatives?
Yes, we do. Yes.
And how do you think about the cost of a false positive in this case?
So there are actually many different cost factors that we associate with. One is the false negative as well, which actually has got much higher than the false positive. So our models tend to be, so we usually try and go for the F1, try and reduce false negatives as much as possible. But the cost factor for a false positive is high enough so that we don't necessarily run into any kind of trouble. So that's essentially how we design it.
So you're not just outputting a confidence that the client will then consume and interpret as they want. You're giving an actionable decision.
Yes, yeah. And there is a variable component to the cost factor as well. And that variable component comes from certain risk coefficients that are actually associated with certain primary features. For example, if the transactional amount is super high, we tend to provide a reasonable high cost factor to it. So there is a variable component to it as well.
So when you say cost, you mean like so for the matrix?
Yes. So basically, if the model is predicting a lot of false positives, or if it's essentially what we do is we penalize the model, and that's the cost factor that this gentleman is talking about.
So just curious, like in real world, you guys do use the F1 and stuff, but you also customize it as per your needs.
No. F1 is always what is used because we do not want to be in a situation where we missed things. So we try to reduce false negatives as much as possible, so which is why we use F1. But even then, we are having a larger cost factor for everything that the model gets wrong, and that's essentially what we're tuning on. All right. Any other questions? If not, I think okay. We are at 7:40, so maybe it's time to Thanks, guys.